Hey everyone, welcome to Professor Long's lectures in microbiology. These videos are intended for use by students who are enrolled in my Biology 2420 or microbiology class at Del Mar College. If anyone else out there in YouTube land finds them helpful, please hit like and subscribe or provide some feedback so I know whether I need to continue doing this stuff or not, or should tighten these up. These videos are being done for my students. I want you to learn the material that I teach, the way that I teach it for my exams. Anyone else out there, you have to learn all the material that your instructor wants you to know. I'm hoping that my simplistic way of explaining these things really helps you understand some of it, wrap your brain around it, and learn it so that you can carry that information in your brain for a long period of time. These videos are done somewhat crudely. I have a cell phone, me, a tripod, and a board. They're all one-shot takes, not a lot of editing. And so any pauses or disruptions or coughs or anything, you guys just forgive me. I'm not going to edit that stuff out. I'm not savvy enough yet to know how to do that. Now, the last lecture that we talked about was a chemistry lecture where we talked about matter, elements, atoms, the subatomic particles, ions, isotopes, ionic bonds, polar covalent bonds, non-polar covalent bonds, and hydrogen bonds, like that form between water molecules. And you should know a little bit more about water, like, you know, the stabilizing temperature of water and all of that. But we're not going to talk about that for now. Now, the last part of chemistry that we need to get across is what is an acid, what is a base, what is the pH scale, and a buffer. You need to know those four things: acid, base, pH, and buffer. And then we're going to talk about four major organic compounds and the roles that they play in cells and in life processes. Okay, I'm going to give you a very simplistic overview of these things. It could be far more complex and detailed than this, but again, I don't believe in giving you all the details up front. We'll learn some of those details now. We're going to set the fundamentals and add detail as we progress. Now, so one way to define an acid, and sometimes some of my chemistry colleagues don't like this, but I don't really care. When we talk about an acid, one way that an acid is defined is any substance that releases hydrogen ions or protons when in solution. Okay? Well, then that begs the question, what on earth is a solution? So before I go any further about what an acid is, we certainly need to talk about what is a solution. Now, the chemical definition of a solution is a uniform mixture of a solute and a solvent. Okay, this is going to be a circular argument, but learn the language. It's a uniform mixture of a solute and a solvent. That begs the question, what is a solute? It is any substance dissolved into solution. Again, these are kind of circular arguments because, okay, I'm using the same terminology, but what does this stuff mean? What is a solvent? Any substance into which a solute is dissolved. Oh my God. This is why chemistry becomes hard, because you're learning all this language, but you don't know what it means. A solution is a uniform mixture of a solute and a solvent. I tend to think of a solute, this is my simplistic way of getting it across to my head. It doesn't work in every instance, but I tend to think of this as the solid stuff dissolved into the solvent, and the solvent is the liquid. Although that doesn't really work 100% of the time, okay? And I know I'm writing kind of small. I think you can see that and read it, yeah. So, if I were to take a glass of water and take a couple of markers and dump them in the water, they will not form a solution. Because what I put into the water, the markers, this solid stuff, does not dissolve. And that's part of the definition. It doesn't dissolve. It sits, it'll look like two markers sitting in water. I don't have a uniform mixture because the markers don't just disperse and become all equally distributed in between the water molecules. Now, if I took some Kool-Aid, and I powdered Kool-Aid and I dumped it, or sugar, and I dumped it into a bucket of water, and I stir it up a little bit, or even if I just wait long enough, all that red powder from the Kool-Aid doesn't just sit on the bottom. It might initially, but if I walk away and I come back a few hours later, the whole jar will like it's uniformly equal in color from top to bottom in all areas. And that's because the solvent, that solid powdery stuff that I put into the solute, the solid powder that I put into the solvent, the liquid, became uniformly distributed and equally distributed throughout the substance. If it were sugar, and I could take a drop with the dropper from the very top of the glass and taste it, and put the dropper all the way at the bottom and get a single drop out and taste that, it would be equally sweet on top as it is in the bottom. It becomes a uniform mixture. So anytime I talk about a solution, it's a uniform mixture of something dissolved into something else. Well, when I take an acid and dissolve it into solution, it's going to release hydrogen ions. So, what do I mean by that? Let me give you a very simplistic idea. Okay? So, I'm going to take a substance. Hopefully this color will show up really well. I'm going to call this substance X. I don't know what it is. And it turns out that each substance X has some hydrogen atoms attached to it. And if I take a whole bunch of substance X with all of these hydrogen atoms, let's say I take 10 of these. 2, 4, 6, 8. I'm going to draw 2 more. So substance X has some hydrogen atoms associated with it. And I have a glass of water, a solvent. If I take these 10 molecules of X and I dump them in here, so I got 10 of them floating around. Actually, before I do all that, if I have the same jar of water and I put a little probe in here that can measure and tell me on some little screen how many free hydrogen ions are floating around. When I say free hydrogen ions, I mean hydrogen ions that are not associated in a chemical bond or in a covalent bond, hydrogen atoms that are in a covalent bond with another substance. I mean, literally, there's a couple of hydrogen atoms floating around in here previously that are not attached to another molecule. They're just floating around by themselves. Well, I have a machine called a pH meter that can measure how many of those hydrogen atoms are there. And while this is not exactly how it works, this at least gets the concept across. So bear with me. This probe is going to tell me, let's say every one of these represents 10 molecules. So really this is 100. I got 10, 10, 10, 10, and I keep adding 10, 20, 30, 40, 50, 60, 70, 80, 90, 100 hydrogen, 100 X's. Before I put X in the solution, I can measure how many hydrogen atoms there are. And let's say there's 300 of these floating around. And they're in here by themselves. Let's say that some of these X's release their hydrogen atoms as ions. Not all of them. Many of them hold on to it, but a few of them release it into solution based on some interactions, so that I get a couple of extra hydrogen atoms floating around freely that have broken off of these X's. This guy gave off his hydrogen atom, and this guy gave off his hydrogen atom, not that one. So that when I go measure it, if I just don't look at the X's, all of a sudden, this number has gone up. As soon as I put X in here, the number of free hydrogen atoms floating in the solution has gone up. Then I know that X must be an acid. Because as soon as I put it in solution, the number of free floating hydrogen ions went up. Meaning that X released some of those hydrogen atoms. It's the only way I can explain it. Before X was in there, I have only a certain number of hydrogen atoms or ions floating around. After I put X in, the number of free hydrogen ions goes up, then X must have released those, X must be an acid. Does that make sense? I think of it this way. If I took 100 guys in blue shirts coming into a room with a basketball under each arm, or let's say a beach ball, they all have a red beach ball. No, since they got a blue shirt, they all have a blue beach ball. 100 of those guys walk in the room. Before they walk in the room, we're sitting in this big empty room like it's a concert, and people are batting beach balls around. Let's say there's 3 beach balls batting around. The beach balls represent free hydrogen ions. When these 100 guys come in, let's say 80% of them release their hydrogen atoms, release the beach ball. Then the number of beach balls bouncing around the room will have gone up. I will get 80 more. Now I have 83 beach balls instead of just 3. I can say that substance X, or the blue stuff, is an acid because the minute it enters solution, some of them molecules release the hydrogen ion. Maybe not all of them, but some of them. We call that an acid. Now, we're going to use the term strong acid and weak acid. When I talk about what a strong acid is a strong acid releases a high number, or sometimes we'll say a high percentage, of its hydrogen ions when in solution. And a weak acid will release a lower percentage of hydrogen ions when in solution. Now, again, I'm not giving you technical chemical definitions, but I'm giving you an idea of what these definitions would really mean so that we can actually kind of understand what's being said. So let's go back to my example. I have 100 guys all wearing a blue shirt, all of them with the beach ball tucked under their arm. The minute they walk in the room, let's say 86 out of the 100 release their beach ball. And I got 14 of them still holding on. But an overwhelming majority released their hydrogen ion when they entered solution. Then that would be a strong acid. It's an acid because it released hydrogen ions. It's a strong acid because a high percentage of them are releasing the hydrogen ion when in solution. Now, let's take 100 guys in red shirts with the red beach ball. If they walk in the room, and let's say only 14 of them release their hydrogen ion, but the other 86 are holding on to the beach ball, then I would have a smaller number of free hydrogen ions. Since a lower percentage of them release their hydrogen ions, we would say it's an acid. It still releases hydrogen ions, but it's a weak acid because a lot of them hold on to their hydrogen ion. Only a few release it. Okay? Now, if I look at this exact same concept, I'm going to talk about a base. And another way to say something that is a base is I can say an alkali. When I'm talking about things that are basic, or a base, or an alkali substance, what that means is it's any substance that removes hydrogen ions when in solution. And a strong base removes a high percentage of the hydrogen ions when in solution, and a weak base, the lower I get on the board, the harder it is to get my hand in the correct position, will remove a lower percentage of the hydrogen ions in solution. What does this mean in practical terms? So let's say I have substance Y. I don't know what Y is, but I got some substance here, some powdery substance, and I want to dump Y into my solution. My solution tells me I have 500 hydrogen ions floating freely. This is not exactly how it works. We're going to talk about logarithms in a minute, but this is just to get the concept across. If the minute that I start dumping some of Y in here, it starts binding up some of the hydrogen ions, and I have a few that don't, but a majority of them bind them up so that when Y is entered into solution, now I only have 100 free hydrogen ions floating around. Some of the Y's don't bind it up, but most of them do. This would be called a base or alkali, because when I put it in solution, it removes the free hydrogen ions. So let's say I have 100 beach balls bouncing around inside the room, and we're having a big party in here like a concert, and 100 dudes in blue shirts walk in, and out of those 100 guys, let's say 80 of them grab a beach ball, and when they catch it, they don't let it go. They take it out of the... Now I've gone from 100 to only 20 beach balls bouncing around. I could say that that's a strong base. It's a base because it removed the hydrogen ions from floating freely to binding them up. It's a strong base because a high percentage of the hydrogen ions were removed when I put it in solution. Now, let's start over and say we have 100 beach balls bouncing around, and I have some dudes wearing red shirts that walk in, and out of 100 of these guys, let's say only 6 grab a beach ball and hold on to it, the others just ignore it. So I've gone from 100 to 94 beach balls bouncing around. I've removed a lower percentage of them. That's a weak base. Weak bases don't remove all the hydrogen ions, just some of them, a small percentage of them. It's a base because it removes hydrogen ions, but it's a weak base. Okay? That's all that we mean when we talk about acids and base. And again, anytime I use the term alkali or alkaline, I'm talking about a base or basic solution. Okay? Now, why do we care about any of all of this? Okay? Why is this important to us? Well, we're going to see in just a second. Let me clear the board, and we'll talk about this. Now, scientists have come up with a way to measure the number of free hydrogen ions in a solution using what we call a pH meter or pH paper, and we can talk about this. So, really the true definition when we discuss an acid is it's the negative logarithm, or when I say pH, we're going to define this term pH. The true definition of pH is the negative logarithm of free hydrogen ions in solution. What in the hell is a negative logarithm? Unless you have a lot of math and understand the logarithm scale, the base 10 scale, that doesn't mean anything to us. So the way that I like to think of pH, so that I can wrap my brain around it, is I think of it as the probability, although this is not a very good way to think about it, and chemists hate this, but what's the probability of finding free hydrogen ions in a solution, especially when I mix something in with it? What's going to happen to the free hydrogen ions, or what's the probability of seeing them? A bunch of them. Well, there's a thing called the pH scale. Let me try to switch markers again, because as I write, some of these markers get more faint. The pH scale goes from 0 to 14. And in the dead center is 7.0, although I may not have drawn that exactly in the middle. I'll try to get it close. 7.0 is said to have a neutral pH. It is neither acidic nor basic. If I go below 7, this would be the acid range. If I go above 7, this would be the base or alkali range. And the further away from 7 I go towards 0, the stronger the acid becomes, or the weaker the acid becomes. And the same is true for the base. A strong base will have a higher pH. If the pH is anything above 7.0, it's basic or alkaline. The higher I go, closer to 14, the more basic or alkaline the solution becomes. The lower I go below 7, the more acidic or stronger the acid becomes. So, if I drop something in, if I form a solution that has a pH of 7.0, the probability of me finding free hydrogen ions in there is not a whole lot. And if there are some in, when I put this substance in there, if it takes one off, it also releases a new one. And if another molecule comes in and removes that one, then it will release another hydrogen ion. So if they take one on, they release one so that the number of free hydrogen ions does not change. Where if if I put an acid in there, as I put it in, it will release more hydrogen ions. And the stronger the acid, the higher the percentage or the higher number of hydrogen ions it's going to release when placed in solution. The stronger the base, the more of the hydrogen ions it will sponge up. This will only pull out a small percentage. This will pull out a higher percentage of those hydrogen ions floating around. That's a simplistic way of thinking about it, but since I'm not that smart, I got to simplify things to understand it. Now, if I list the pH of several substances, okay, I'm going to give you the pH of several substances. So let's say I take, I don't know, potassium hydroxide, okay, KOH. I think this has a pH of about 9, if I remember properly. I could be a little off. But pancreatic juice. Juice from your pancreas. The pH of pancreatic juice is about 7.45. I have water. pH 7.0. I have urine. pH 6.5. Tomato juice, pH of about 4. And stomach acid, a pH of about 1.0. I could ask you, of these substances, which ones are acids and which ones are bases. Since these have a pH above 7, these are our bases. These are all acids. This has a neutral pH. If I asked you which of the following substances would be the strongest base, potassium hydroxide. I think the pH is around 10. It might even be higher. I gotta look it up. I forgot. Which one is the weakest base? Pancreatic juice. Which one is the strongest acid? Stomach acid. Which one is the weakest acid? Urine. These are not acids. These are bases. So urine is an acid. It has a pH below 7.0, but it's the weakest of the ones listed here. This would release the fewest hydrogen ions when placed in solution. This one would release the most hydrogen ions when placed in solution. And that makes a great test question. Which of the following substances would remove the most hydrogen ions when placed in solution? Potassium hydroxide. Which of the following substances would remove the least hydrogen ions when placed in solution? Pancreatic juice. These don't remove any. Which of the following substances releases the least hydrogen ions when placed in solution? Urine. Releases the most? Stomach acid. Weakest acid, strongest acid, weakest base, weakest base, strongest base. Okay? So we can ask the question either way. Which of the following solutions would be the strongest base? Which of the following substances would remove the most hydrogen ions when placed in solution? They're the same answer. Which of the following substances is the weakest base? Which of the following substances would remove the fewest hydrogen ions when placed in solution? Okay? And we can say the same thing for the acids. So now, we have a basic understanding of what an acid is, what a base is, and what the pH scale is, and what the numbers can basically kind of tell us. Again, it's on a logarithmic scale, so every time we go from pH 1 to pH 2, it's actually a massive increase in the number of hydrogen ions released going from pH 2 to pH 1. It's based on the base 10 scale, and you got to multiply everything by tens instead of going in a linear fashion. I'm not going to get into that detail. You can understand logarithms when you go into math. Now, one last thing we need to talk about when we're talking about pH is what is a buffer? It's any substance that resists changes to pH or in pH. It resists pH changes. For example, let's say I have a solution here, and I can probe this solution, and I know that the pH of this solution is about 7.45. And I have a whole bunch of acid over here, a bunch of hydrogen ions. And I start to dump hydrogen ions in here. But every time I dump one in, it kind of gets removed, bound up. So that even though I put a whole bunch of acid in here, and I should see the pH start to lower and lower and lower, the pH stays relatively the same. Let's say I put enough of this stuff in here that the pH becomes 7.449. Then this substance must be a buffer, because no matter how much hydrogen ion I try to add, it's resisting changing solution. Now sometimes buffers can get overwhelmed and then start to turn acidic, and you do that when you do certain titrations with potassium hydroxide in chemistry. And the same would be true if I made this a base. If I added base in here and the pH only went up a hair, if at all, then I would say this is a buffer. It's not going to change pH no matter what I try to do to it within a certain range. Anyway, so that's all that a buffer is. Why do we care about acids and bases and buffers? Okay, I'm going to give you one simple example. We haven't talked about proteins yet, but we will in a minute. And before I get to proteins, let me just tell you this. Proteins are long chains of amino acids. So I have a whole bunch of these little beads on a string. Each bead represents what we call an amino acid. And the whole thing is called a protein. It turns out that maybe two of these amino acids have a little side group that if I put them close together will form a chemical bond. And because they're floating around in water and mixing around like spaghetti in a boiling pot, they might form a bond. So I go from a straight chain of amino acids to a folded chain. Now that might bring two other amino acids close together, and over time, my protein will start to fold up, almost like those little round-looking shades you put in your car. Once you start to twist them, they just collapse down on each other. Well, eventually this protein can fold up into a three-dimensional shape. And every time it does that, we actually give off usually a molecule of water. One of these will give off a hydrogen atom, one will give off a hydroxyl group, and they form some water. And so if I since it's taking a hydrogen ion or hydrogen atom off here and forming water every time I fold up, what happens if I flood this molecule with a bunch of hydrogen atoms? I'm sorry, hydrogen ions. What if I put this protein that's folded up in what we call the natural form of the protein, or the natured form? When a protein is in its natured form, that means it's folded up into the shape it's going to go in. If I flood it with acid, the likelihood that one of these hydrogen ions is going to bump into here and break that bond by binding here, then what happens is I can unfold the protein by adding acid. And the protein becomes denatured. When a protein is denatured, it doesn't function. It doesn't perform the function. It takes on a three-dimensional shape that determines its function. And so, when we have the natured form of a protein and it's functional, if I flood it with acid, I can denature the protein and stop it functioning. So in some instances, too many hydrogen ions, too strong of an acid, is detrimental to the molecules that are going to be performing the functions inside my cells. And so we sometimes call these free radicals. They're little substances or things in the universe that can disrupt other molecules that are performing functions in our cells. And so and some of the vitamins we take remove some of the free radicals, helping our cells out. And so when we talk about pH, and the same would happen if I put too much base here, a hydroxyl group, an OH group would bind and denature the protein. So when we talk about acids and bases, the reason they're important is that they can have an impact on the functioning of other molecules. Proteins require a small pH range in which to be able to be folded up into their perfect shape so that they can perform their functions. If I change the pH by making it too basic or too acidic, the protein denatures, stops performing its function. And so that's why our cells function within a narrow pH range. And that's going to be true of all the cells we're going to talk about in microbiology. This is why acids can kill things and bases can kill things, certain microbes and certain cells in the universe. All right? So listen, we've done enough of this. There's one more video I have to do on chemistry, which is going to be the 4 major organic compounds, but I hope you understand acids and bases, the pH scale, and buffers, and why they're important to us. All right? Hope you had as much fun as I did. I hope you learned something. See you on the flip side of the next video.